All right, let's just remind ourselves for a moment where we were. And that is that we were talking about the structure of the atom. And we talked about how classical physics, the classical mechanics, classical electromagnetism, failed to explain how the electron and the nucleus hung together. And I said that the clues about how to solve that conundrum actually came from a different area of discussion, and that's this wave-particle duality. And so remember that I said we're going to put aside that discussion of the structure of the atom all the way until Monday, next Monday. And, pardon? No class Monday. We're going to put it aside all the way till next Wednesday. Thank you. Okay. You sound surprised. You're not. There is no, it's a student holiday on Monday. Okay? All right. So, and we're going to talk about the wave-particle duality of light and matter, get clues from that area of discussion, and we're going to apply those clues then to solving the structure of the atom next Wednesday. Okay. Now, we started on this discussion by talking about the wave-like nature of radiation. And to illustrate that, we did this two-slit experiment where we saw an interference pattern. And we talked about how that interference pattern arose because of the property of superposition of waves. That is, if you have waves in the two same points in space, their amplitudes superimpose, or they add. And because some of those amplitudes are positive and some are negative, depending on the relative phase of the waves, you have constructive or you have destructive interference. And specifically, what we were trying to understand is, in the two-slit experiment, why we had this line of bright spots, dark spots, bright spots, dark spots. And we analyzed it by drawing these semicircles, which represent the wave front kind of sneaking through this little pinhole here, this slit, emanating equally in all directions. So these semicircles here represent the crest of the wave. So the distance here between these crests is 1 lambda, is 1 wavelength. And when we look closely, and could we dim the lights in the front here? If you look closely, what we discovered is that all points along this line, right, all points along this line constructively interfere. That is, we have waves that are at the same place in space, and the maxima and the minima are in the same place in space. And so that's going to lead to a very bright spot here on the screen. The amplitude is going to be twice as high as it was in each of the individual waves, and we get this very bright spot. And we realized that along this line, the difference in the distance traveled by the two waves that are constructively interfering was 1 lambda. And then we did so for this line here. And we discovered that all along this line, we had these two waves in phase. All along this line, we had constructive interference, which, of course, imaged as another bright spot. And when we analyzed it, we found that the difference in the distance traveled by the two waves was 2 lambda. Right? And likewise here, all along this line, we had constructive interference, imaged as a bright spot. And we recognized that in this case, the difference in the distance traveled by the two waves was 0 lambda. And given that pattern, we then concluded that we had to have that there was a general condition for constructive interference. That is, if you had maximum constructive interference, the general condition that had to apply was this, that the difference in the distance traveled by the two waves was an integral multiple of the wavelength, where this integer n could be 0 or 1 or 2 or 3 or 4, All right, and it's actually symmetric here along the center of the two slits. So you'd see the same kind of interference pattern up here. All right? And so we call this interference feature right here, we often call it the zero order interference feature. We call this one, when n is equal to 1, the first order. We call this one the second order interference feature. And in between the very bright spots on that screen, what we have are dark spots, here, here, and here. And what I'm going to ask you to do in recitation section next Tuesday, is to look at what condition has to apply in order to have these dark spots, which result from destructive interference. And of course, when you analyze that, you're going to see, say right here, you're going to see the crest, the maximum of one wave, at the same point in space as the minimum of the other wave. And you get destructive interference, maximum destructive interference everywhere along that line. And what you'll do in recitation next week is actually to figure out what the condition is for destructive interference. All right? And that's going to be n plus 1/2 times lambda. All right? Okay. So it is this observation of these interference phenomena that are characteristics of the wave-like nature of anything. In this case, the wave-like nature of light, of radiation. On Friday, what we're going to do is we're going to see the same sort of interference phenomena, a property of waves. We're going to say that same sort of interference phenomena be observed from particles, from electrons. All right? So this diagram you're going to see once again on Friday. All right? And they will use that to demonstrate the wave-like nature of particles, electrons. All right. So that's our evidence for the wave-like nature of light. And now what we're going to do is we're going to talk about the other behavior of light, and that is the particle-like behavior of radiation. And I forgot to get out my notes. All right. So what is that evidence? Well, soon after Thomson's discovery of the electron, there were some observations being made of something called the photoelectric effect. And this was very curious. Photoelectric effect is simply, you have some metal here, and you shine some light on that metal. And what happens is that an electron is ejected. All right, so metal, light coming in, electron comes out. But the frequency of this light that's coming in, this frequency nu, we talked about frequency the other day, has to be greater than or equal to some threshold frequency that I'm going to call nu naught. So in other words, if I come in with radiation here that is got a frequency that is less than nu naught, well then, no electrons come off of the metal. Right? Well, another way to kind of plot that observation is to, maybe we could raise the screen here for the moment. Okay. Another way to plot this is to just plot number of electrons versus the frequency of the radiation. And so if you're at low frequency, there are going to be no electrons that come off. But then when you get to some frequency nu naught, all of a sudden electrons are going to come off. And the number of electrons that come off is going to remain constant as you increase the frequency of the light. And typically, this frequency of the light that causes these electrons to be emitted is in the ultraviolet range. All right, well, this was a curious observation in the late 1800s, very early 1900s. And scientists just started to measure everything about these electrons they possibly could measure, because they just didn't understand the effect. And one of the things that they measured is the kinetic energy of the electrons. All right? So here I'm going to plot kinetic energy, Ke, and they measured the kinetic energy of the electrons as a function of the frequency of the light. So again, at low frequencies, there's no kinetic energy because there's no electrons. But then here, at some frequency nu naught, all of a sudden electrons come out. And lo and behold, these are points just representing the individual measurements, right? Lo and behold, as you increase the frequency above nu naught, the kinetic energy increased, right? It increased and looked directly proportional. The kinetic energy looked directly proportional to the frequency of the light. Well, let me tell you, that was a big mystery as far as classical physical ideas were concerned. That was a big mystery. Because in the classical physics that was understood at that time, the kinetic energy of the electrons, Ke, as a function of the frequency of light, well, that classical physics would predict that that kinetic energy were independent of the frequency of the light. There was nothing in the known classical physics, classical electromagnetism, that would allow the frequency of the light to be related in any way to the kinetic energy of the electrons kicked off. There was no reason for why bluer light, which has a higher frequency, bluer light would eject electrons, and redder light, which has a lower frequency, would not eject electrons. And classical physics also predicted that the kinetic energy of the electrons should be dependent on the intensity. I'm going to call it I, the intensity of the light. And kind of general this sort of dependence. That is, the brighter the light, the more kinetic energy these electrons ought to be kicked out with, right? In other words, the brighter the light, the more energy you were putting into that metal, and therefore the electron should be kicked out with more energy. Right? That's what classical physics was predicting. But the measurement, go in the lab and you do the measurement showed that the kinetic energy was independent of the intensity of light. This is the experiment. Right? It had nothing to do with the intensity of light. The kinetic energy remained the same, no matter how bright that light was, no matter how much energy you were sticking into the system. Now, what changed here, as you put more and more energy, or as you put more and more intensity, what changed was the number of electrons that came off, but not their kinetic energy. Okay? All right, so this was another conundrum here in terms of being able to explain it with the known classical physics at that time. So these data were around for a few years before Einstein saw it, took a look at it. And he looked at these plots of the kinetic energy versus the frequency of the light, and then he looked at it for, say, this is the data for metal B, right? Here's the data for metal A. In all cases, kind of looked like it was linearly dependent on it. And the only thing that was seemingly different for the different metals was the threshold frequency here. So what Einstein did, real leap here of intuition, is that he went and he fit a straight line to this data. Well, he did a better job fitting a straight line than I did. All right, he fit a straight line here. Y equal mx plus b, right? No problem. Where kinetic energy is y and x is mu, right? And he looked at that, calculated the slope, and he looked at it, and he goes, finally, very interesting. Because what was so interesting here was the value of this slope, right? The value of m. The value of this slope here was equal to 6.626 times 10 to the minus 34 joule seconds. Right? No matter what metal he looked at, the value of the slope was 6.626 times 10 to the minus 34 joule seconds. Hey, so what, you say? Well, it was very interesting to Einstein because just a few years before, there was a gentleman who was analyzing what's called Blackbody Radiation data. And let me just explain this a little bit to you. You're not responsible for it. But what's a black body? Well, let's just, for a simple example, think about the burner on your electric stove. We'll consider that to be a black body. What you know is that when you turn up the voltage, that the temperature starts going up, and at some point the temperature gets high enough such that the burner glows a little bit dull red, right? And then if you turn up some more, it gets hotter, the burner glows a little bit redder. That's the black body radiation. You turn it up some more, the burner glows orange. Frequency going up. You turn it up some more, and you better not do this, the burner starts glowing yellow. And then if you could, and you probably can't, turn it up some more, it ultimately is white, all frequencies. Okay? Now, what scientists had been doing is that they had been analyzing the intensity of that radiation from a black body as a function of the frequency, and they did it for lots of different temperatures. All right? So this is our black body radiation. I'm plotting the intensity here. And so they dispersed the radiation. They analyzed it as a function of frequency. And what they saw was a curve that looked kind of like this. And this temperature here, we'll call it T1. That was for some temperature T1, a low temperature. This isn't in your notes because you're not responsible for this. I'm just trying to make the importance here of this slope, or just trying to illustrate the importance of this value for the slope in the photoelectric experiment. And then at a higher temperature, at a higher temperature here, T2, the intensity got bigger, but also the maximum shifted to higher frequency. And at temperature T3, so here now T3 is greater than T2, is greater than T1. Frequency shifts even to a higher frequency. Okay, that was the observation. So this is dull red, red, orange, etc. Well, Planck was trying to, along with a lot of other people, understand those curves. And he came up with a model. And the model said that materials, these black bodies, these materials had oscillators in them. And these oscillators were emitting radiation. These oscillators were responsible for giving off this radiation. And he also added another twist to those oscillators in that those oscillators were quantized, that they could only emit discrete packets of energy. And using that basic idea and something called statistical mechanics, he was able to calculate the shapes of these curves. So out of his calculation, and so this green here is going to be a calculated curve here for t equal 1, calculated curve here for t equal 2, a calculated curve here for t equal 3. So he got the shape right, but he didn't get the magnitude right. And he said, well, how do I get the magnitude right? Well, what he realized is that in that formulation, what he had to do is to multiply the frequency of the oscillators by this constant, m, or this constant that is called h, Planck's constant. So where does Planck's constant come from? From this. Hey, that's it, right? It is, in a sense, a fitting constant, right? There isn't any derivation of Planck's constant. You can't sit down and derive Planck's constant. It is our observation of the way nature works, right? So that's where Planck's constant comes from. And so you can imagine Einstein's surprise when he analyzed these photoelectron data. And lo and behold, out from the data comes the same constant that Planck had found. And Einstein realized that there must be something really very fundamental about this H, about what is now known as Planck's constant. So he pursued. And what he did then is he just wrote down the equations here for that straight line. Whoops. He wrote down the equations for the straight line. So that's kinetic energy is equal to nu. That's my x. The slope is h. And he found that the intercept here was minus h times nu naught. All right? So this will be then plus the intercept, or minus h times nu naught. All right. So that was the equation of the line he fitted through the data. Now, he also realized I got energy units on this side. Hey, I better have energy units on this side. So if this is a frequency here, then h must have the units such that h times nu, well, this has got to be an energy. Right? And since this is the frequency of the light coming in, hey, this energy, E, that must be the energy of the incident light. And here is where this equation E equal h nu comes from. All right? This is it. This is where this equation comes from. What it is telling you is that the energy of the light is proportional to the frequency. This was the first time that there was any indication that the energy of the light had anything to do with the frequency of the light. The very first time. And what E equal h nu ended up being thought of is as a particle of energy, as a packet of energy, as a quantum of energy, as eventually it's going to be called a photon, right? The photon, this particle or packet of energy, is given by its frequency times this constant, this natural constant, h, Planck's constant. So you could have here any frequency of light you wanted, but the energy of that light only comes in chunks given by this quantization constant h times that frequency. All right, I'll explain that a little more in just a moment. Okay. Well, likewise, this h times nu naught here, that better be an energy also. And so what that h times nu naught is the threshold energy. Since nu naught was the threshold frequency, h times nu naught better be the threshold energy. And let's try to understand that in terms of an energy level diagram. All right? So I'm going to plot here energy. And this electron that's bound to the metal, before we shine any light on it, I'm going to let its energy level be represented here by this line. So this is the electron bound to the metal. Okay, way down here. And what we know now is that it takes some energy, h times nu naught, to rip that electron apart, to pull it off. And so I'm going to draw another energy level up here, which is going to represent the energy of the electron free from the metal. So I'll call it electron free. Okay? And the amount of energy that we have to put in to get it out is this threshold energy, h times nu naught. Okay? This energy here is like an ionization potential, which you're familiar with, right? The energy required to pull an electron off an atom or a molecule is the ionization potential. Well, this is like an ionization potential. It's really the ionization potential, except since it's coming off of a metal, historically we call it something else. It's called the work function, and we give it often the symbol phi. All right, but phi and h times nu naught, hey, they're the same thing. It's the energy required to rip the electron off. Okay, and so what we know is that the packet of energy that you send in here has to be at least this amount. Okay? So in other words, if you come in with a photon, and the photon has this much energy, E sub I equal h naught, you can rip the electron off. All right? But you have to have at least this. Now, you can come in with a photon that has more energy than that. All right? E sub I from here to here. But if you do, then the rest of this energy here, the rest of this energy goes to the kinetic energy of the electron. So if you come in with exactly the energy, the electron's ripped off, but it doesn't move away from the metal. If you come in with a little bit more, well, the electron's ripped off the metal, but it actually moves away then from the metal. All right? And so in this case, and in all cases, we got to conserve energy. So the incident energy of the light, right, from here to here has to be equal to h nu naught plus the kinetic energy, right? Or if I turn this around, the kinetic energy is equal to the incident energy minus h nu naught. All right? This is an important expression. You need to know it. I won't give it to you on an exam. You don't have to memorize it, though. You just have to reason. You have to reason here, conservation of energy. You can draw this diagram, okay, and figure it out. Okay. Now, another very important point here that I'm going to emphasize is that you absolutely, positively, no question, have to have a photon of at least this energy to get the electron off. What you cannot do is you cannot have, for example, a photon with half of this energy, 1/2 h nu naught, or what you can't do is have two photons come in with a half of this energy and make that electron come off. All right? You have to have one photon to make this electron come off, and it has to have the frequency nu naught. All right? That's the particle-like nature of the radiation. The fact that you can't, even though you have the same total amount of energy here, The fact that you can't have two, right, to pull the electron off, you have to have it one, and it has to have at least this quantum, at least that packet of energy. All right, that's very important. All the problems you're going to do, if one photon comes in, you're going to get one electron off as long as that photon has h times nu naught of energy. Okay? Okay, great. So now what we got to do is we have to do our own. Yes? Yes, if the energy of the incident photon is, if this energy here is twice the work function energy, yes, the electron will come off, and the excess energy that doesn't go to the metal to pull the electron off goes to the kinetic energy of the electron. And so if this incident energy is twice the work function, well, then the kinetic energy of that electron will be equal to the work function. Okay? I'm sorry? Two electrons won't come out. That's a good question. What she asked is, if I put twice the amount of energy here with one photon, will I get two electrons out? No. Absolutely not. Okay? That's the quantum nature, or the particle nature of the radiation. Okay, let's do our own photoelectron experiment. All right? Yes, question?
I just had a quick question. So how did these results pertain to that graph that you showed us earlier?
Uh-huh.
The one with the intensity and the kinetic energy, this one? It's kind of like, it's static.
Okay, those graphs up here, kinetic energy versus the frequency of light, those were the predictions from classical physics. All right? Kinetic energy independent of frequency, kinetic energy increasing with the intensity of light. Those are predictions from classical physics. How I got them, how I knew about them, is something that we're not going to talk about because it's wrong. Okay? So it's best at this point not to go through the logic of how I got that. But maybe after you had 802, right, it will become obvious to you. Okay? Okay, good question. Okay, let's do our own photoelectron experiment. And so now we need the camera here. Okay, and now what I also need is, let me get this started here. What I also need are two volunteers to help us do this experiment. Who want, come on down. Somebody else want to come? Okay, come on down. Is the camera on?
Yeah.
I don't know. Come on. Okay. All right. So I have two volunteers here. And, oh, I forgot to tell you that I need to do something. So you got to stay up here for a moment. I forgot to explain something. My fault. Sorry. All right. Okay, what we're going to do, and maybe you want to turn around, and I forgot to tell you something here. All right, what we're going to do All right, we're going to use this device here. This is an aluminum plate. And you're going to see it here on the side walls. That's a picture of the device we've got up here. This is an aluminum plate. And that aluminum plate is mounted to a metal rod. That's that blue rod. And then there is a needle here in that blue rod, and it's mounted on a pivot. So it moves very easily. So what we're going to do is we're going to put some excess charge on this metal plate. And when we do that, that needle is going to deflect. It's going to deflect because those excess charges, the electrons, are going to run down that metal rod and then onto the needle. And since these electrons repel each other, and this is a very low friction pivot, this needle is going to move. Right? And then what we're going to try to do is we're going to try to do the photoelectron experiment. We're going to come in and shine some UV radiation on this plate and see if we can eject electrons. All right? That's what we're going to do. Okay, so now I got my volunteers who are going to do this. Who wants to be the charger? Who wants to be the discharger?
I'll be the charger.
You'll be the charger. Okay, all right. So this will be your weapon. Okay, you hold that, you hold that. Keep your fingers on the yellow plastic. This is going to be your weapon, the UV light. So you can just, I'm going to need you in a moment. All right, so just stand by. Okay, so what's your name?
Dawn.
Dawn? Okay. Dawn, what you need to do is you need to take that lucite rod and rub it really hard on the fur. And what that's going to do is the fur has some natural oil, and he's going to transfer a little bit of the natural oil onto that rod. And there's some stray electrons around and some negative ions around, and they like to be on that oil. But then we're going to contact that rod with the aluminum plate, and the electrons will go onto the aluminum plate, okay? So you got to rub this really hard, all right? And then you got to go and touch that and put the electrons on, and you should watch the needle move here, okay? Now you got to touch it on the edge, actually. Good. All right. Well, you charged it a little bit. Hey, that's not bad. Okay. Now take the rod again and rub it really, really hard. Really hard. Really hard. Okay, and get it, touch the end of the plate there.
Where's the end?
Touch the edge of the plate. And my microphone came off, and it's going all the way through here. You see this? That's the first time that ever happened. Okay, this way, this way. Okay. Okay, you got it pretty charged there. Okay, touch the edge of the plate. Whoa, fantastic. Okay, now we need the discharger. You got to come right here and shine the UV light on the face of that. Okay, got to get a little closer. Maybe turn your hand this way so that people can see it discharge. Whoa. Okay. Fantastic. Okay, try it again. Come on, charge it up. Really hard. Touch the end of the plate.
I think I took all the electrons out.
No, okay. This way, this works the best. All right, all right. Touch the edge of the plate. Let's get it. Hey, fantastic. Okay, maybe it's just a little bit more. We can get more electrons on it. Hard, hard, hard. Really hard. Okay. All right, all right. Okay, charge it up. Oh, okay, discharger, discharger. All right, fantastic. Okay, what you saw is when the UV radiation then was incident on that aluminum plate, the electrons were emitted, right? And then the needle deflected back. All right, now we got to do this one more time. But this time, yeah, and my thing is falling apart here. But this time, why don't you come over here? What's your name?
Jenny.
Jenny, come on over here, all right? If you can. Okay. And this time, after you charge it up, I'm going to hold this. I'm going to hold this glass plate between the light and the Pyrex plate between the light and the aluminum plate, and that's going to prevent the UV radiation from going through, and so it shouldn't discharge. Okay? Okay. All right. So go ahead. Let's charge it up one more time. You really do have to rub that oil on there. Oh, okay. Okay, really hard. Right. Okay, touch it up here. Fantastic. Now I'm going to put the light there, and now we're going to shine it. Oops, it's already discharging. All right, you got to do it one more time. We got to do the control experiment here. Okay, really hard. It's a little bit humid out today, so it's a little bit harder to make this work.
Careful with the UV. Don't point it at your leg.
Okay. All right. Okay, a little bit harder. Done. Get it up there. Okay. All right. Touch the side there. Hey, good. Now.
Wait.
Ooh. Okay. That's pretty good. Fantastic. All right. So we blocked the UV radiation. Electrons didn't jump off. Hey, this works. Thank you very much. Let's give them a hand. Thank you very much. All right. So this photoelectron business, hey, it's really real. Okay. So what I want to do now is I want to just work a couple of problems. And here's the first problem. All right, what it says is how many photons at a radiation wavelength of 1 picometer do you need to supply a pulse of energy that's a 1 joule pulse, say from a laser. It's a pulse laser. Suppose you want to supply 1 joule of energy in this light pulse. Okay? So that's what the problem says. 1 joule in a pulse. Now, how do you work a problem? Lots of ways to work a problem. Sometimes I like to draw pictures. 1 joule, hey, that's my 1 joule, right? I want 1 joule of energy. But I'm told that I have radiation that is a wavelength of 1 picometer. That's 1 times 10 to the minus 12 meters. That's the wavelength of my radiation. And I'm asked how many photons do I need? Well, what do you know about a photon? Hey, we said that the energy of a photon is equal to h times nu. That's 1 photon, the energy of a photon. The units here are joules. Implied is joules per photon. Okay? And so I know the wavelength. I don't know the frequency here, but I know the relationship between wavelength and frequency, right? Frequency is equal to c over the wavelength, all right? And so I can then calculate the energy, and when I do that, it's 1.99 times 10 to the minus 13 joules per photon. Carrying 1 more digit then is significant because this is an intermediate step in our calculation. And now if I want a pulse of energy that's 1 joule, and I have each photon has 10 to the minus 13 joules per photon, well, that's 1 joule divided by 1.99 times 10 to the minus 13 joules per photon. Well, you can calculate that. It comes out to be 5 times 10 to the 12 photons, right? That's what I will need then in my, that's the answer then. Let me just write that down. Okay. Let's work one more where we can understand the, this is important because you need it for your homework. Here's the problem. You've got power of a radiation from a continuous laser. So you turn on your laser, you got power. What's power? Where power is energy per unit time. we're going to use in our unit system, the unit is power is watt. Right? A watt is a joule per second. It's how much energy is delivered per unit time. And we're told that we've got radiation of 3 milliwatts. That's 3.0 times 10 to the minus 3 joules per second. The question is, how long will it take for a total energy of 1 joule to be supplied? Well, 1 joule divided by 3.0 times 10 to the minus 3 joules per second. Hey, that's going to be 330 seconds. All right? All right, and then rushing through this, one more. It says how many photons at a radiation wavelength of 1 picometer again, how many photons will be, or how many photons per second have to be delivered if the power of the radiation is 3 milliwatts. Okay? So the power is 3.0 times 10 to the minus 3 joules per second. The radiation is 1 picometer, but we already calculated how many joules there are in radiation per photon with wavelength of 1 picometer. That's 1.99 times 10 to the minus 13 joules per photon. All right? Joules cancel, and that means we're going to have 1.5 times 10 to the 10 photons per second, because each photon has this much energy. This was the power. The rate at which we're delivering the energy, we're going to have this many photons per second coming out if the photons have that wavelength of 1 picometer. Okay? Great. See you either this afternoon or on Friday.